Okay, so we'll start. Today's talk will be by Stephen Melczer from the University of Pennsylvania. So he'll present on his joint work with Bruno Salvi on effective analytic combinatorics and several variables.
Yeah, thanks very much for coming. Thanks very much for the invitation. So this is work that I mainly conducted during my PhD thesis, which was at the University of Waterloo and at the École Normale Supérieure in Lyon. And I was sent these really nice instructions that said you shouldn't assume anyone's an expert in the field, and you should give lots of motivation and examples and things like this. So I will talk about the results that we got, but a lot of this talk is going to be motivation and maybe to get people here interested in working on some of these problems from your points of view. So we'll learn today what analytic combinatorics is, what analytic combinatorics in several variables is, and sort of about effective methods there. And I was unclear whether or not this was actually the differential algebra seminar or the symbolic numeric seminar, so I put in examples from both. So we'll start with a bit of an introduction, and we're going to start the introduction with a thought experiment. So imagine you're a modern-day undergraduate student, and you took calculus or linear algebra, and you saw that there are all these great tools. So there's Mathematica, Maple, Sage, and you can put in your math problems, and they just spit out the answers for you. And you think that's fantastic, whatever I come across in mathematics, then I can just put it to the computer can tell me the answer. Maybe you even take the Symbolic computation course here, which seems to be Math 650, because you want to learn more about it. And of course, we all know in this room that your dreams are going to be crushed because there are all these results that you run up against. So a particularly nice one is, this is one way of stating many of these undecidability results, which is if you have an arbitrary expression that you get from the constant 1, the variable x, sign an absolute value, then it's undecidable to test equivalence to 0. And this is basically for reasons related to Hilbert's 10th problem. So what do? We don't just give up and say that we can never do anything on the computer, right? Of course, we just restrict what we actually consider. So, of course, if we're trying to decide equalities or inequalities with integers or rational numbers or integer polynomials, we can decide these kinds of things. And another example, which is still extremely classical, but somehow a little bit less trivial, is the field of algebraic numbers. Because if you're dealing with, say, integers, you're basically storing the actual integer. But with algebraic numbers, you're using sort of an implicit representation, right? So you store an algebraic number as some minimal polynomial and maybe some isolating region in the complex plane. And then if you want to add them or multiply them and check equality to 0, you can do that using elimination theory, so resultants, Kronecker bases, etc. So this is, of course, this sort of general framework we have in computer algebra. Now let's go and think about combinatorics. So in particular, we're going to look at enumerative combinatorics. So our main object is going to be some sequence, and you can think of this as counting the number of objects in a combinatorial class, so the number of objects in a tree of a certain kind with n nodes, or a lattice path with n steps, or etc. Often you can get these kinds of sequences in the analysis of algorithms, so the nth term could be the runtime of an algorithm on its input of size n. And our main sort of object is going to be the generating function of this sequence. So a priori, hopefully everyone here has seen this before, but if you haven't, it's just a formal series in a variable, say z, where the coefficient of z to the n is the nth term of your sequence. And the idea is that combinatorial definitions often automatically translate to generating function specifications. By combinatorial definition, I mean, for instance, like a binary tree is a node followed by 2 other binary trees. And so because you have this decomposition, you can get something, say an algebraic equation on your generating function. And in fact, generating functions were introduced to study certain types of sequences. So many people would point to the work of de Moivre in the early 18th century as sort of the introduction of generating functions, which is series that are actually used because of the properties of their coefficients, not just as thinking of them as series of analytic functions. So for instance, in his very famous work in 1718, it's also one of the rare works you can actually read because it's in English, it's not in Latin at the time. Basically because de Moivre loved Newton and was at Cambridge and he wanted to suck up to Newton, so he wrote in English. So basically what he's saying here is that you have a linear recurrence relation of order 2, and the generating function will be rational. So this is how you would write a second order linear recurrence back in 1718. And in fact, in 1730, de Moivre showed that if you have any linear recurrence with constant coefficients, if you have a sequence that satisfies that, your generating function is going to be rational. So nowadays, a lot is known about, about different classes of generating functions and the types of sequences they have and where they occur naturally in combinatorics and computer science. So for example, if you have a rational generating function, well, if you're enumerating the words in any regular language, you'll get a rational generating function. These form an important subset of rational functions. And from a computer algebra point of view, there's a very natural way to encode this, right? You just can encode the numerator and denominator. Say we're working with, polynomials with, or rational functions whose numerator and denominator are polynomials with integer coefficients. You can store this on your computer. If you want to deal with algebraic generating functions, then an important class here is unambiguously generated context-free languages. Also, many types of trees have algebraic generating functions for basically this sort of recursive decomposition that I alluded to.
So in rational regular function languages, you don't get all regular languages, do you?
Every regular language has a rational generating function, but there are rational generating functions that do not count regular languages.
Okay, so it's not identical.
No, it's not identical.
And
this
how
is
you
a
represent
subset.
the numerator and denominator? What is the representation? Binary or what?
Well, so I'm assuming that you have, say, integer polynomials, and so then you just need to store some finite list of polynomials, or of integers, which are the coefficients, and then you can encode those integers in binary or however you want to on your computer.
I mean, the regularity of the language depends on how you encode, right? Base 10, base 2 may be different.
Yeah, so assume you give me a regular language and that you give me just a grammar in terms of unions and stars and things like this. Then you can basically directly translate that specification into a rational generating function.
Okay, so the language is not encoding the rational.
This is not encoding the language. This is encoding the number of words of a given length.
Oh,
so the coefficient of x to the
number
n.
of words. Okay,
Yeah, exactly.
Okay. Then
Yeah.
then it's okay.
Yeah, so you could also have a multivariate rational function where you're actually trying to encode the language. But no, here I'm just talking about counting. Yeah, that's a good point to make. Any other questions? Okay. So if I do a similar thing, if I count the words of given lengths in context-free languages, then I get algebraic generating functions, if they're unambiguously generated. Actually, there's a very nice paper by Philippe Flageolet where he proves that you have ambiguous languages, so any grammar must be ambiguous that implements them basically by looking at their generating functions and showing they're transcendental. And again, there's a natural encoding, so very analogous to what we have for algebraic numbers. You can store these by minimal polynomials and then a sufficient number of initial terms of the sequence, which is the power series equivalent of storing like an isolating region. Something that comes up quite a bit in combinatorics as well are the class of D-Finite Functions. And these are functions whose coefficients satisfy linear recurrences with polynomial coefficients. And so just as an example, so a D-Finite function is one that satisfies a linear differential equation with polynomial coefficients. So the generating function satisfies a linear differential equation. The coefficients satisfy a linear recurrence. And as a quick example, if you take a look at this generating function here, the central binomial numbers squared, then you can prove by looking at asymptotics, for instance, that this is transcendental, but of course, because of the recurrence relations on the binomial coefficients, it satisfies this simple differential equation. And again, there's a natural encoding, which is just the differential equation, say a linear differential equation that satisfies plus some initial conditions or initial terms of the sequence. Now, what I'm interested in a lot is asymptotics. So we basically take a sequence specified by its generating function satisfying, being in one of these classes encoded like this.
Is the D-Finite only univariate or what?
Yeah, for me, when I say D-Finite, I mean a univariate function.
Okay.
Yeah. There is a notion of D-Finiteness in multivariate functions, but just for me, right now, everything is univariate. We'll get to multiple variables soon. So if I'm interested in asymptotics, there are some technicalities, but technicalities aside, if I have a rational function and I know its numerator and denominator, it's basically automatic to find asymptotics of the coefficient sequence. In fact, you can get an explicit expression for all terms of your sequence up to after some finite number of terms. Same thing for algebraic functions. It's a little bit more difficult. You need sort of like path tracking techniques and things like this. It's actually an interesting symbolic numeric problem, but it's more or less automatic to get asymptotics. D-finite functions, on the other hand, it's still unknown, because of reasons I'm about to describe, whether or not you can take your sequence encoded by the differential equation in initial terms and tell me what the asymptotics are. So why is this? Let's look at a couple examples. So a specific combinatorial problem that I like looking at is lattice path enumeration. So you start with some number of steps, so say the diagonal directions here, and some region, say the first quadrant, and you want to count the number of walks that start at the origin, take these steps, and stay in this region. So for instance, on these steps, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 walks of length 3. So it turns out that you can show the generating function of this satisfies this differential equation, or it's annihilated by this differential operator. And so, as mentioned before, the coefficient sequence satisfies a linear recurrence relation with polynomial coefficients. So again, as an example, the coefficient sequence satisfies this linear recurrence with polynomial coefficients. So there are methods to find basically an asymptotic basis of solutions. So you know that you can compute something so that the asymptotics of the sequence you're interested in is a linear combination, an R-linear combination of two terms in this case, because you have an order 2 recurrence. And so really this is kind of misleading because each element of the basis is actually like sort of an infinite asymptotic expansion, but these are the leading terms. So I know that my leading asymptotics will be some constant times 4 to the n over n plus another constant times negative 4 to the n over n squared. And then the difficult part is that it's a linear combination of these and I need to know what these constants are. In particular, suppose I'm interested in whether or not my sequence is always positive. I would need to know whether or not the coefficient of this is 0.
Excuse me, wouldn't you need 3 basis functions instead of 2 because it's...
No.
Why do you think it's 3? Why would you think it's 3?
So think if you have order 0 recurrence, then you're saying like q to the n is 1.
Oh, this is
right?
order 2, right?
Yeah, so it's order 2.
Doesn't depend on the degree of the coefficients.
Yeah, no, yeah, okay. But there is this kind of weird thing where when you translate between the differential equation and the linear recurrence on the coefficients, then you have to take into account the coefficient and degree. But here, yeah, this is,
okay, so
when you're doing that, no, that's a good
you're
question.
doing the wrong thing.
So in particular, if we want to find dominant asymptotics, we would say that, okay, it's like 4 to the n over n times some constant, and we need to know what this constant is. In fact, you can actually find these constants rigorously to any accuracy you want. And this is a good place to bring that up because a lot of the pioneering work was done by the Jodosky brothers here in New York. And so in this case, you could go and you could, there's a very nice implementation of this in a Sage package by Mark Mazarova, who is another PhD student, Bruno Salvi. And you can use his package to take in this basis, and it would tell you that this constant is 0.636 ... And in fact, it's equal to 2 over pi, which you can calculate in a way we'll see in a second. But of course, so here, maybe you don't know the constant exactly, but you basically have asymptotics, right? You have it up to some, with as many decimal places as you want. But things could be worse. So now we'll go to a different example. So this same thing being in the first quadrant, but we have this set of steps. And now it satisfies an order 15 linear recurrence with polynomial coefficients. So you have 15 basis elements. Your first 3 basis elements, and here it's really more honest because it's showing you that you actually have, each basis element is really an asymptotic expansion. So you have the 3 that look like this, and then you have 12 other ones, but they're sort of asymptotically smaller. And so these recurrence relations and differential equations, I should point out, were computed in a paper by Boston, Chizek, Van Hoy, Cowers, and Pesch that was published last year. And so what you can do is you can write the number of walks at some constant times 3 to the n over n, square root n, plus some other constant times this basis element, plus some other constant times this basis element, plus other things that grow like this. But the key thing here is that this constant actually turns out to be 0. And so you might think that the walks grow like 3 to the n over square root n, but actually they grow like 2 root 2 to the n. And of course, if you wanted to numerically compute this, you could rigorously show that this constant is 10 to the negative 10 or 10 to the negative 100, but you can never conclude that it's 0 because you don't know a priori bound on what you have to check. I mean, it's good intuition to say that, okay, it should be 0 if it's 0 to 100 decimal places, but you don't actually know. So this is sort of the heart of the undecidability or decidability of asymptotics, is whether or not you can show these coefficients are 0 or not.
What is the phi?
Which?
Phi of t is
Oh, here?
Yeah.
Okay, yeah, so I'll get to this right now. So in this paper, basically these authors were interested in finding asymptotics of these walks and also trying to solve the differential equations that come up. And so what they did is they basically represent the solutions of the differential equations. So they represent the generating functions in terms of 2f1 hypergeometric functions. And so in particular, they have a representation for this constant, but they show that this is 0 if and only if you have some integral which is equal to 1, and the integrand is this crazy thing involving rational functions and 2f1 functions. So they say that, okay, we can show that it actually grows like this, which is what everyone sort of knows it grows like, but you have to decide this, which is very difficult to do. And again, you can numerically approximate this, and you can say that, okay, it's basically 0.99999, but to prove that it's 1,
This is still not proved, right?
this is still, well, now it's proved. So basically, using other means, myself and Mark Wilson were able to find asymptotics of these walks. And so when you actually prove asymptotics, then you would prove that this constant is 0. So as a corollary of our work on asymptotics of these walks, we prove that this is equal to 1 because it must be.
I see.
So we have these crazy,
roundabout way.
yeah, we have these corollaries that give all these crazy integrals of 2f1 hypergeometric functions, which we don't really care about, but but in a roundabout way, we did prove these things, yes.
I see.
So where's the idea of this phi come from? I mean, the expression is...
So basically, they get the differential equation that it satisfies, and then they factor it into differential operators of order 1 and 2, I think. And then they try and solve these differential operators, and when you solve these differential operators on low orders, that's where these hypergeometric functions come up. Yeah. So I should say it's a very non-trivial thing to do. And actually, this paper, it was delayed several years because they were trying to prove these asymptotics, and they couldn't do it because they ran into these problems of finding the constants.
Non-trivial thing to do for a, in what sense?
To find these solutions, well, you have to, so to find the differential operators, to prove the differential operators, you use creative telescoping, which is just, for some of these models, it's very computationally intensive. Then you have to factor them, which is also not easy, into these certain, factors of certain orders so that you can try and solve these factors. And then you have to actually go through and solve. If you factor your operator into like a linear operator times degree 2 operator, then you actually have to go and solve it. So there's many steps, some of which are computationally intensive, some of which you have to sort of... So I don't know, I'm not an expert in factoring differential operators, but as far as I know, it can be quite a difficult problem to do.
For a computer, but not for, the human interaction is minimal here, right? Or not?
Yeah, yes, but I think you need to be clever. If you just told your computer to do it, it would probably take too long. You have to be clever in what you ask your computer to do.
And why can you factor in types of factors that you mentioned?
Sorry?
Why can you factor?
Because it happens.
It just happens. Okay.
Yes.
So is there any physical meaning now that you prove C1 is 0, then the integral has to be 1, right? For this particular phi, right?
Yes. So
what is the
what's the significance that this integral is 1?
Yeah, right.
I have no idea.
I mean, it's a probability distribution or what?
I guess, yeah, sure, it is a probability distribution if the integral is 1, but what it measures, I have no idea.
Okay. So how general is this trick? Suppose I come up with a constant, like something like this integral.
Yeah.
And I want to check whether it's equal to 0
Yeah.
or equal to some constant. Can you find asymptotic so that you can use your technique?
So this is an interesting
way to
problem. So let me just hold on for 10 seconds. So we show that this is 0, and we find actually asymptotics for all these for many similar walks in the first quadrant. And what do? So we have these 3 classes of functions: rational, which sits inside algebraic, which sits inside D-Finite. And actually, we're in this special case where we have something called as a G function. So basically, it's a differential equation that has only regular singular points. So it has nicer singularities and its coefficients have slightly nicer asymptotics. And so what we did to prove asymptotics in lattice path models is we introduced a new class called rational diagonal. And finding asymptotics of these rational diagonal functions, which are specified by multivariate rational functions, we were able to actually compute asymptotics and give these constants. Now, if you want to work in general and say, I have a differential equation, so some function that satisfies a differential equation, and I want to find asymptotics, I want to find what these constants are, you would have to take your G function and write it as a multivariate rational diagonal. But it's actually still open how this class sits inside this class. So basically, every rational diagonal is what's called the globally bounded D-Finite function. And that's very easy to see, and that's a very large subclass of the D-Finite functions. But it's been open, so there's a conjecture, it's called Krystal's conjecture, it's been open for 20 plus years, whether every globally bounded D-Finite function is a rational diagonal. And that's a very difficult question that people are very interested in. And if you could resolve it this way, I would love that because it would make my work a lot more impactful because we could answer questions about general D-Finite functions by looking at these rational diagonals. So this is the general setup. Things are easy to decide here, it's a bit harder to decide here, and then in between, we have this new class that maybe we can get a better handle on. And the way that I was interested in this class is because there was actually a problem where people could not compute the asymptotics because you ran into these decidability problems, and we specifically could because of this. And because of that, that's when I started studying this class, and now that's what led to basically my whole PhD. So are there any questions about the setup before we go on?
When you talk about generating function, you're using the monomials as basis.
Yes, exactly.
What about other bases like exponential generating functions?
Yeah, so you could, I mean, again, if you have the exponential generating function which satisfies, which is algebraic or satisfies differential equation, then you're just working with the function, right? So you could find asymptotics of the function, and then you could multiply by n factorial and get asymptotics of your original, of the sequence that you would care about. For instance, if you started with the exponential generating function. So here, I'm assuming that I have a function, and I want to find asymptotics of its coefficients in the monomial basis. But
so your starting point is the differential equation then?
Yes, exactly.
Okay.
Exactly. Yeah, so you could also think for these classes, for D-Finite and rational, it's very natural to also encode it by the linear recurrences with either constant coefficients or polynomial coefficients. But for algebraic, it's actually not so clear what exactly that corresponds to on the coefficients. So every algebraic function is D-Finite, but by representing it as linear recurrence, you're sort of using a bigger class to represent these things. Any other questions? Okay, so now we've been introduced to the major classes. Let's start looking at these rational diagonals. So we have a multivariate rational function. So now, sorry, I switched. Because I'm going to give complexity results later, I need to talk about degrees, so I want to say a D for degree. So now I'm in n variables, and I'll look at the kth term, so I apologize for that. So I have a multivariate function, which is a rational function, so it's polynomial g divided by polynomial h, and it has a power series expansion at the origin, and just to save sanity, I'll often use this multi-index notation. So if I have bold quantities, these are multivariate quantities. If I have bold z to the bold I, then this just means z1 times I1, z1 to the power of I1 times z2 to the power of I2, etc. And so we have this big multivariate power series expansion. We want to get a single sequence out of this. And so the most natural one, one of the most natural ones, is the so-called diagonal sequence, which are all the terms where the exponents are equal. So as a simple example, if I take this right here, the coefficient of x to the I, y to the j is actually just the binomial coefficient I plus j, choose I. This is what the binomial theorem will tell you. And so if I take the diagonal sequence, this is the constant, the coefficient of x to the 1, y to the 1, coefficient of x squared, y squared, etc. And so I get the sequence of the central binomial coefficients. So the diagonal of this is the generating function. The diagonal sequence is the central binomial coefficients. And then the generating function of that is the generating function for the central binomial coefficients. Something that will be important later is that all the coefficients here are actually not negative. These things actually come up in more areas of mathematics than you might expect. So for instance, they appear quite frequently in number theory because if you have what are known as binomial sums, these are diagonals of rational functions, and binomial sums appear quite frequently in number theory. So the most famous example of this, which is cited in many talks, is so-called the Apéry's sequence, which is related to his celebrated proof of the irrationality of zeta 3. So that sequence is the diagonal of this rational function here. And so the survey that people most often use to read about this is very beautiful work, very beautiful paper. It's called A Proof That Euler Missed by van der Putten. And in that he has an exercise which says, be the first on your block to prove by a two-line argument that zeta 3 is irrational. What do? You have two sequences. You want to show they satisfy some algebraic relation, which is not so hard, and then you want to find asymptotics of one of them. And this Bn sequence is exactly the diagonal of that rational function that I just showed. And in particular, you don't even need to find asymptotics. You just need an upper bound on asymptotics, and you really just need an upper bound on the exponential growth, which is actually quite a bit simpler to get.
Do you know why at all people consider knowing whether it's rational or not?
Knowing
Z of 3.
Oh, I think I don't know. It's like a central question in algebraic number theory, but I have no idea why people really care about it, to be honest.
So it might be a thing in itself, right?
Sorry?
It might be a thing in itself.
What is the thing?
Just a technical question.
I guess. I don't know. I mean, there's hundreds of years of work with thousands of papers on it, so I assume it's important, but the specific reason I can't remember back to my number theory class.
So the zeta n's are all conjectured to be irrational, right?
I think so. So the
Zeta
even ones
2
are
or
known.
Zeta 2 is pi or something?
Yeah, so the even ones are known to be irrational. That was already done by Euler.
Right.
Zeta 3 is known to be irrational, but after Zeta 3, I think all the odd ones are not known whether they're rational or irrational. But there are some results, like, I think there's some finite set, like between Zeta 5, Zeta 7, and Zeta 9, like at least one of them is irrational, or something like this.
Right. Or even stronger, non-transcendental. That's the
Yeah. So maybe I should know this. This is like a fundamental thing that every mathematician should know. Maybe why the zeta numbers being irrational is so important, but
Maybe not.
maybe not.
And why two-line argument?
Well, so one line is to show that it satisfies this, and one line is to find this asymptotics, I guess. So of course, you have to set everything up using a priori's beautiful argument to conclude that it's irrational because of showing these two things, but that's the idea, is that when you set it up, when you think about it in a certain way in terms of asymptotics of these two sequences, then all you need to do is show some simple relation and find asymptotics. So you set, after this hard work, then you will get a proof. And I mean, this whole survey is not that long, it's only like 5 or 10 pages at most.
Very dense.
Yeah, it could be dense. Yeah. And so, lattice path enumeration, I already talked about this. This is something that I think is a very interesting subject, and it's very nice for the study of different generating functions because you get a lot of different generating functions appearing, like rational, algebraic, D-Finite, algebraically D-Finite, so satisfying nonlinear differential equations, hyper-transcendental, which are ones that don't satisfy algebraic differential equations. And as an example, so you often get very nice rational diagonal encodings, which is how we were able to prove asymptotics. So for example, if you take this north, south, east, west set of steps, and again, you're in the first quadrant, this is the diagonal of this quite simple rational function.
So the multivariable rational functions, do they also correspond, have a regular expression language? To counting?
Yes, so, well, yeah, so if you have a multivariate rational function, then the coefficients will satisfy linear recurrence with constant coefficients, multivariate linear recurrences with constant coefficients. So you can think of these as counting words in regular languages. Something I will say though is that if you have a multivariate recurrence with constant coefficients, that does not mean you have a multivariate rational generating function. In fact, you can have hypertranscendental generating functions with that. So it's not a two-way street anymore, but the one way works. So if you change the set of steps, you change there are models for this which this doesn't work, but for many models it does work, and if you change the set of steps, then you can change the rational function, but it's sort of predictable what happens here. And this is still not so bad. So the only thing that's really bad is this term here, but this term here actually encodes basically how you can take a single step. For instance, the step 1, 1 here is encoded by x to the 1, y to the 1, and so this sort of has a combinatorial meaning, and other than that, it's not so bad.
So you're saying that you can actually write down?
Yes, so if you look at models in the first quadrant, there are many models that are trivial or models that are equivalent to each other. So there are basically 79 models that are really of interest to people. 56 of them.
That's Singer's work, is that right?
Sorry?
Is that Mike Singer's work?
Michael Singer has worked on this. He has a recent paper in Invenciones on it. But the first two combinatorialists who popularized this were Marnie Mishna and Mireille Boschi-Milou in Vancouver and in Bordeaux. And so they're the ones who showed that there are these 79 models. 23 of them have D-Finite generating functions, so you could approach them using these techniques. The other 56, it's still open for most of them, but people believe they have non-D-Finite generating functions, so you can't write them as rational diagonals. And so for basically all the 23, there's a few that are algebraic, and actually this thing kind of breaks down, but for the non-algebraic ones, so there's 19 of those, for all of those, there's an automatic method where you give me the steps that I will give you this rational function. Now again, this is D-Finite, so you could find an annihilating differential equation, but it looks like this, and it's pretty messy, right? So it's order 5,
How do you know that's the minimum one?
Yeah, I don't actually know if this is the minimal order. And of course there's also...
I mean, you wrote minimum order.
Oh, okay, in that case, these guys probably proved it was the minimal order. So these guys are good at manipulating generating functions, and they proved it, I think. So it's order 5, its coefficients are polynomials of degree, 20 or something like that, with big integer coefficients. So I don't think that you can really look at this and get any good intuition, even dealing with it on a computer can be a little bit messy, at least compared to something that looks like this. And then again, you could say, okay, maybe I want to solve my generating function in terms of special functions, and you can do that. That's one of the things they do in this paper. But again, you get some kind of crazy expression in terms of iterated integrals of 2f1s with rational parameters. And so I don't think that you can really look at this and say anything too deep, whereas the rational diagonal expression is quite compact, and it comes up naturally. Actually, the way you would compute the differential equation is through creative telescoping from the multivariate rational function, or an equivalent representation.
So is there a sense in which the diagonal is the dominant term in asymptotics or no?
So yeah, so if you have a multivariate sequence, you have many different, or a multivariate function, you have many different sequences.
Right.
And so what I'm going to talk about today is asymptotics of the diagonal sequence, but you can also find asymptotics of different ways of going off to infinity. And basically, so what I'm going to talk about today, it directly works if instead of looking at, for instance, a, n, n, you could look at, I don't know, a, n, 2n, 3n, 5n, or whatever. So you can basically pick a sort of ray, an exponential ray, and go along that ray. So everything I'm going to talk about today follows exactly the same. If you want to look at like a, n, n squared, then it's a little bit of a different story, because this sort of behaves quantitatively different. But you can sort of, if you go off linearly in any sort of exponential direction, you can, what I'm about to say about asymptotics, you can do basically the same thing.
Sorry, can I ask what the three variables are, the x, y, and t? Are x and y like the endpoint, and t is the number of steps?
X, y, and t.
I think on the previous one before.
Here? Yeah, so this is something that's interesting. It's that there isn't really a good combinatorial interpretation for this multivariate function. Like the diagonal counts the number of walks, but the things off the diagonal, no one really knows what they count. Yeah, so it's not like this is a multivariate generating function for something. It's that the diagonal of this is the univariate generating function for the number of walks. So that's a very good point, though, that you might think that because this actually arises fairly naturally through something called the kernel method, which is a very useful technique, and it sort of is a combinatorial construction, which is one of the reasons that you have such a nice rational function here. But just because this arrives combinatorially doesn't mean that it actually represents something.
The walks always begin at the origin?
Yeah, you can begin them from other points, and you get just some small modification.
But then that sort of initial behavior that might be not.
But asymptotically, it's kind of negligible.
That's right.
And actually, something I've done in other work is you can start with parametrized beginning point, and then you get asymptotics which have your beginning point, say ij, in the asymptotic constant. So it won't be in sort of the exponential growth part of it, but it'll be in the constant. And what you get is you get something called the discrete harmonic function because of sort of the recurrence relations that these walks satisfy. And then people in probability apparently really care about finding nice examples of discrete harmonic functions. So I do have some work about finding these things for probability theorists to use by taking parameterized beginning point. So yeah, you can, if you modify the beginning point, it's not so different. You can also look at walks which go back, say, to the origin, so they start and end at the origin, or they go back to different axes. And if you want walks that end on an axis or go back to the origin, there's actually, you can again get an explicit diagonal expression for that.
Without this extra parameter, number of walks, you mean just number of walks of length n? Is that
so right here is just the number of walks of length n that stay in the first quadrant.
Okay.
You could also look at the number of walks of length n which stay in the first quadrant and begin and end at the origin. This would be a different sequence. And there's actually a strong link between, you can find a rational diagonal which is very similar to this. It's basically just this times 1 minus x times 1 minus y. And that's to go back to the origin. And if you just wanted to go back to the x-axis, it would be this times 1 minus x. And if you want to go back to the y-axis, it would be this times 1 minus y. So I don't really, I could give a whole other hour-long talk about how these lattice path things work. It's a very beautiful subject and has nice connections, but I want to go more a bit onto the computations. So I think I'll just...
And so how non-unique is that expression?
Yeah, of course. This is another thing, is that of course, there are many expressions whose diagonal is this sequence. You can just take anything with 0 diagonal and add it onto here, and you'd get a rational function whose diagonal is your sequence. So it's a very interesting problem, I think.
It has to be a rational function.
Well, so it doesn't have to be rational. You can define the diagonal as long as you have a Taylor series, right? But
you advertise it as some nice representation.
Yes.
So then maybe you want to stay within that.
Yeah, so in terms of explicit computations, it's always easier if you have a rational function. I'm going to talk a little bit about the theory of how you get asymptotics, and what I'm going to say there actually works for any meromorphic function, multivariate meromorphic function. But when I'm doing my things about computation later, about symbolic numerics, of course I need rational functions, because I need to say things about the zeros of polynomials. But yeah, it is a very interesting, sort of still fairly open problem to say that, okay, what's the simplest multivariate rational function that encodes my sequence? And of course, what's the simplest is also an open problem, because simplest could mean many different things depending on what you care about. Okay, so these appear in many different places, but I'm taking more time than I thought, so I'm going to skip that, but they appear a lot. Okay, so how are we going to find asymptotics? We use this thing called Analytic Combinatorics, and I don't expect anyone here to really know a lot about it, so I'll go quickly over what happens in the univariate case. It's a very beautiful subject, and so I recommend, if you're interested, to read this fantastic book by Flagellate and Sedgwick. So the idea is that there are deep links between analytic properties of a generating function and asymptotics of its coefficients. And this all basically comes from the Cauchy integral formula. So if I have a power series, univariate power series, then the Cauchy integral formula implies that the nth term, the nth coefficient here, can be represented by some complex integral. So if you remember that from complex analysis, that's great. If you don't, then it's not really important. The idea, the only thing you need to realize is that this is an analytic object. And so if we want asymptotics of our coefficients, we can look at asymptotics of this analytic object. And this is a very classical subject in complex analysis that goes back hundreds of years. So there's lots of results on finding asymptotics of these kinds of integrals. So suppose that I have a sequence. Typically, what will happen is that you'll have some exponential term. So maybe something, 2 to the n, 3 to the n, or 1/2 to the n here. And then something sub-exponential, so n squared or n log n, etc. And so there are two main principles of analytic combinatorics that you can get by playing around with these integrals. So the first is that the location of your function's singularities will determine this exponential growth, which is sort of the coarsest measure of growth. So as an example, if I take this function here, of course, this is just a geometric series, so the coefficient is 2 to the n. So this has exponential growth, 2, or 2 to the n, and you have a singularity in z is 1/2. And in fact, that's what really happens. Every singularity of your generating function gives some asymptotic contribution, and the exponential part of that asymptotic contribution is just 1 over the modulus of the singularity. So if you look at this generating function, which is the generating function for Catalan numbers, you have a singularity in z as a quarter, and your asymptotics grow like 4 to the n, the exponential part. And so you can see it's very direct to go from the singularity to the exponential growth, which again tells you quite a bit of information about your sequence. Then the second principle is that the type of singularity you have there determines the sub-exponential growth. And by type of singularity, I mean, do you have a pole? So are you, for instance, does it look like you're dividing by 0? If you have a pole, you have a first order pole, so like a simple 0 in the denominator, or for instance, a 0 of degree 2. So if I keep my singularity in the same spot and I go from a simple pole to a pole of order 2, then my exponential growth will stay the same because it's in the same location, but the sub-exponential growth changes from a constant to a polynomial of degree 1. So other types of singularities would be algebraic singularities, so square root or cube root, logarithmic singularities, things like this.
So these principles are theorems, or?
Yes, they're theorems.
They're theorems.
They're theorems. If you have singularities that behave in many different ways, so algebraic, algebraic of any degree, or logarithmic, or algologarithmic even, so algebraic times logarithmic, or logarithmic with an algebraic inside it, then there are sort of many papers on this where you can basically look up a table and say, it behaves like this is the asymptotics. So Flagellate and Olisco sort of wrote the first really big paper on this, and it's kind of exploded ever since then. That was maybe in the 90s or so. So here, if I keep a square root singularity, but I move from z as a fourth to z as a fifth, then my exponential growth changes, but the sub-exponential growth basically doesn't change. There's just this factor, and that's because I changed the z in the radical, but I didn't change the z in the denominator, so we get the scaling factor. So that's the basic idea. And so what you want to do is you want to find the singularities whose asymptotic contribution is the biggest, so they have the biggest exponential growth. And these are going to be the ones who have minimal modulus. They're the ones closest to the origin, because the exponential growth is the reciprocal of the modulus. And there's something that actually helps you quite a bit, which is usually referred to as Pringsheim's theorem, although Borel might have not about it earlier. And it says that if you have a power series with non-negative coefficients and finite radius of convergence, then you'll have a singularity. And furthermore, one of the singularities with minimal modulus is real and positive. So that's very helpful because what you can do then to find asymptotics is you could just start at the origin and go along the positive real axis until you get to a singularity. And then there might be other singularities at the same modulus, so you have to look for those ones. So you basically go around the circle of that modulus and find the other singularities. And then you just look at the type of the singularities, if they're algebraic or logarithmic, and then you look up these tables and you say, okay, the singularity looks like this, these are the asymptotic contribution. Then you add everything up. So it's very powerful. It's very easy to try and automate, at least in the easiest cases. There are some interesting things that arise, and so because this is at least partly the symbolic numeric seminar, I have something here that people in the audience might be interested in, and that's that we're interested in finding singularities of the same modulus. And so the simplest case is if you have a rational generating function, right? So you have something that looks like p to the x over q to the x, and so the singularities will be zeros of the denominator. And so basically what you want to do is you want to find all the singularities of minimal modulus. And so what you need to do is you need to take roots of this polynomial and say when they have the same modulus. And as far as I know, so the separation of roots of a polynomial has been well studied, but separation of the moduli of roots of a polynomial is actually much less studied. And this is very important here, because this is exactly what you need to do. So just as a quick example, because I'm behind, so the height of a polynomial is the maximum bit size of its coefficients, say an integer polynomial with integer coefficients. So suppose I have an integer polynomial and I take 2 roots of that polynomial, then there are good separation bounds, going back to Mahler and others, on the roots of a polynomial. So the lower bound on the moduli of alpha minus beta, so assuming alpha is not equal to beta. So there's still a little bit open about this exact thing in the exponent here, but basically you know sort of the order that you have to check that these are equal to conclude that they're actually equal or to separate them. But when you're looking at the moduli of zeros, so the modulus of one root minus the modulus of another, if it's not 0, how big must it be? This is still quite open, and this actually leads to this is the worst step when you're trying to find asymptotics of these generating functions. So if you could give a better bound here, you would actually improve the complexity of all the algorithms that try and find asymptotics. So if you have 2 algebraic numbers, their moduli are also algebraic, and so you can use a polynomial that the moduli satisfy to give a lower bound, but that's not so good. So it's basically in the exponent before you had negative HD. So if you use this on the moduli, you get negative HD cubed, which is quite a bit worse. So there's this paper from 2017 by Bruno Salvi and others that say that if you have alpha and beta real, then you can separate by 2 to the negative HD plus D squared. But this is not so strong, right? Because it just means that you have one that's positive and one that's negative. Because if they're both positive, you're just separating the actual roots. Or if they're both negative, you're both separating the actual roots. So as far as I know, other than these results, it's still pretty wide open, and it would be quite impactful if people could improve it, and I know there are some experts in the room here. And if you're interested, this paper by Salvi and the others was in the actually in the Mathematical Monthly, and it gives some good history of this area.
This last paper is in AMN?
Yep.
Uh-huh.
Yeah, so it's a nice survey as well. Okay, so now let's move on to this, how this goes for the multivariate generating functions. And so the overall analysis is more difficult, and so I'm not going to give full details, but I'm just going to try and motivate sort of the constructions and get to the actual things we need to compute. And then we can talk about actually computing those things, because that's probably what people in this room are more interested in. So we have this multivariate rational function, which is analytic at the origin. And let's let the domain of convergence of our multivariate power series be script D. So we want to try and carry things over from the univariate case to the multivariate case, but of course the problem is that univariate is so restricted it's not always clear how you generalize things. So the singularities of this rational function, again, are just given by zeros in the denominator. So it's an algebraic set, but it's now a higher dimensional algebraic set, positive dimensional algebraic set, which are the zeros in the denominator. This is often called the singular variety of the rational function. And so points that are on the boundary of the domain of convergence, these are called minimal points. And these are the ones that are actually coordinate-wise closest to the origin. Or their moduli, there's no point whose moduli is coordinate-wise smaller than the point that you're interested in. And so this is sort of the generalization of the points closest to the origin in the univariate case. But there's a difficulty now. So in the univariate case, especially if you have a univariate rational function, or even if you have a univariate meromorphic function, there's only a finite number of singularities that are closest to the origin. But here you're dealing with a positive dimensional algebraic set. So there will actually be an infinite number of minimal points. And this does kind of make sense because, as was pointed out before, if you have a multivariate Taylor series, this encodes many sequences, basically an infinite number of sequences, right? So this set of singularities must say something about the asymptotics of all these sequences. And so that's why, morally it should be more difficult, that it's encoding a lot more information. But we're still just interested in one specific sequence. So what we are going to try and do is take this infinite set of points and refine them to some finite set, where again we can look at the way our function behaves there, and that will give us asymptotics. So again, the sequences that we consider will have nice asymptotics. So basically they will be like some algebraic number times, so the kth term will be some algebraic number times k to some rational number times some algebraic number to the k. And so in the univariate case, if you had a minimal point, so point closest to the origin, the 1 over the modulus of that point is equal to the exponential growth. Here, you actually just get an upper bound on the exponential growth. And so the natural thing to do is to say which of these minimal singularities give us the best upper bound, and then hopefully there's a finite number of them. And if this bound is tight, then doing some local analysis, like looking at the type of singularity, might tell us what the asymptotics are. So the exponential growth, again, is the sort of most dominant part of the growth of the asymptotics. So what we want to do is we want to minimize this upper bound on a subset of the singularities, right, among the minimal points. And extrema occur at so-called critical points of this map. So if you've taken a course in differential geometry, the simplest case is when the set of singularities is a smooth manifold. If you haven't taken a course in differential geometry, think of it back to calculus. When you want to minimize a function, you set the derivative equal to 0 and solve for these critical points, right? So it's very similar, except now you're not taking a function from the real numbers to the real numbers. You're taking a function from some set, some fixed set. And so you need to do a little bit of differential geometry there. But the idea is the same. And the simplest case, when your set of singularities is a smooth manifold, then you can write down an explicit algebraic equation that the critical points satisfy. So if you didn't follow what I was just saying, just imagine I want to find the points that satisfy these algebraic equations, and there's some reason why it's natural to consider these equations. And if you're saying, okay, what is a smooth manifold? Just assume that h and its partial derivatives don't simultaneously vanish. That would mean that we're in this situation. So as an example, if we take this rational function, then, okay, you want a singularity, so you want the denominator to vanish. And then there's only one equation here, which is that the derivative with respect to x times x, which is negative x, is equal to the derivative with respect to y times y, which is negative y. And if you solve this system, you get to point 1/2, 1/2. And it turns out that 1/2, 1/2 is minimal. And in this case, it's pretty easy to see because if you have 2 points whose moduli are less than 1/2, you can't add them together and get 1. So this strongly suggests that the asymptotics grow so the kth term grows like 4 to the k times something sub-exponential. And in fact, if you know the asymptotics of the central binomial coefficients, it's 4 to the k over root pi k. So this is actually the exponential. So we found singularity that's on the boundary of the domain of convergence, and it gives us the right sort of exponential growth. Now the question is, can you always get asymptotics if you have something like this? And the question is, usually you can. Again, when you're dealing with singularities and multivariate functions, things can go really crazy. So I'm dealing with a restricted case here, so we can pretend that everything is nice, but in general, things can get more difficult from what I'm about to say. So basically, from our point of view, from a computer algebra point of view, we have a rational function with some finite set of smooth critical points. So I have an algebraic system, the one I just put out, the critical point system, and I'm assuming it has some finite set of singularities. I just want to check which ones are minimal. So I just want to check which ones are on the boundary of the domain of convergence, or which ones are, they're moduli coordinate-wise closest to the origin. And so the difficulty is that minimality is a semi-algebraic condition, right? I'm interested in saying something about the moduli of the coordinates, not the coordinates themselves. So this makes it harder to deal with computationally. Something that really helps you, though, is just like in the univariate case, there was this Pringsheim theorem, there's something called being combinatorial in the multivariate case. So we'll say that a rational function is combinatorial if every coefficient in its expansion is non-negative. And so if you're combinatorial, a singularity, so you have a point that's a singularity on the boundary of the domain of convergence, if and only if when you take the coordinate-wise modulus, this is also a singularity and on the boundary of the domain of convergence. So what that means is if I want to show that this is minimal, well, I can show that this is minimal. And to show that this is minimal, it's just enough to look among all the points that have positive coordinates. So now it's actually much simpler, because instead of basically taking a line segment from the origin to my point and then looking at every point given by this coordinate-wise modulus, so taking sort of a product of circles for every point here, if you're in this combinatorial case, you just have to look at the line segment from the origin to this point with positive coordinates. And of course, in general, you can't just write them down explicitly, but if I had a point with it and I explicitly could write down the coordinates, then to test this, it's very easy. I just introduce a new variable, t, and I just check if there's a solution for t in 0, 1 here, which corresponds to checking the line segment. So in general, these will be algebraic coordinates, so you'll have an algebraic system instead of just writing them explicitly, but it's the same idea. And so here, you check the line segment, say, okay, it hits a singularity, it's not minimal, but here it doesn't, so this is a minimal. So minimal critical points, when they exist, they often determine the exponential growth. And when they do, just like in the univariate case, the type of singularity you have determines the dominant asymptotics. So now you can't have an algebraic branch or a logarithmic branch, it's just a rational function. But because you're dealing with a positive dimensional algebraic set, you have a geometry. So the type of singularity now says, are you locally a manifold? Are you the transverse union of manifolds? So maybe a union that looks kind of like this. Or a tangential union, so like a union that looks like a line in a parabola that just touches it. That's a much harder case to deal with. Or you could look like a cone or many other kinds of singularities, right? Singularities of multivariate functions, very big theory. So suppose we have a rational function which has non-negative coefficients, that the set of singularities is a smooth manifold, so HM's partial derivatives don't simultaneously vanish. There's some finite number of minimal critical points, and one extra condition on the geometry, which is called being non-degenerate, which I don't want to talk too much about, but this is, I can tell you more about it later, but it's just kind of a technical condition. So the idea is that if you satisfy these conditions, you can and you can determine the minimal critical points, then you know exactly what the asymptotics will be. There's some automatic formula that you can translate to get the asymptotics. And furthermore, these three assumptions are actually generic. So if I fix the degrees of my numerator and denominator, then, for all rational functions with these degrees, except for those whose coefficients come from some fixed algebraic set, these will be satisfied. Now, of course, these things come from applications, so just because something is non-generic doesn't mean it never comes up. In fact, just because these are all generic doesn't mean that they're sort of equally important. So there are many applications actually, maybe, a quarter of the applications I've seen where you don't have a smooth manifold. So you really want to be able to work to remove this, right? But almost everything that I've seen, maybe even every application I've seen, you do have this technical condition of being non-degenerate. So, of course, even though these are generic, you want to try and remove some of them more than others because they do often come up. And I should say that in the theory, removing this is very difficult theoretically, so the theory still hasn't been fully worked out, but removing this has been worked out theoretically, so you can relax this quite a bit. In terms of previous work, so the overall theory was developed by, it goes back quite a while to people like Bender, Richmond, Gao, etc. In terms of packaging it all together into a big theory, a lot of the work was done by Robin P. Mantle, who's my supervisor at Penn, Mark Wilson, who's my collaborator in Auckland, and Yuli Brizhnikov, who's in University of Illinois, Urbana-Champaign. They sort of developed the underlying theory, and if you're interested, they have this textbook about it. The one thing about this textbook is that it takes a very high-level view in terms of Morse theory, so it's very actually difficult to go through. So many people have tried to read it and have it's been an obstacle because it can be quite hard to understand what's going on, and the authors also admit to that. So if you are interested in this thing, I would recommend looking first at my PhD thesis because there are several chapters in there that just give a pedagogical introduction. So they're not research chapters, they're just teach you about the theory chapters. So Robin P. Mantle, together with Tim DeVries, who was his PhD student at Joris van der Hoeven, they gave an algorithm in the two-variable case using ball arithmetic. They did not give any complexity. Their argument was quite restricted to the bivariate case, and if you have a bivariate diagonal, this is actually an algebraic function. So the class of bivariate diagonals and algebraic functions are equal. So you could actually just find the minimal polynomial and then compute asymptotics that way. So I think the idea was that hopefully this could be generalized to more variables, but it really hasn't been done yet. Alex Rychev had a SAGE package he developed. He was a postdoc with Mark Wilson in Auckland. So it can compute these critical points for you and some asymptotic contributions, but it can't prove that anything is minimal. So it can never really prove asymptotics. Basically, you need to know everything yourself, and then it can help you compute these contributions. But it is quite useful. I used it before we developed our own software. So the main result from my PhD thesis, or one of them,
may I ask a question about the So you mentioned no complexity results a couple of times.
Yes.
Could you clarify what you mean by complexity result?
So to say that, so this is what I mean by complexity result. So suppose I have a rational function whose coefficients have bit size at most h in degree d, then to compute asymptotics takes this many bit operations. This is this type of thing I mean by complexity result.
And so is this an analysis of the worst case or
Yes.
the case that...
So, well, okay, so I should say that if you look at this, so here's our result. So under the assumptions I said before, so combinatorial and these other three assumptions, there's a probabilistic algorithm computing dominant asymptotics of the diagonal in basically hd to the 4n bit operations. And so really, because of several reasons, you would expect something that looks singly exponential, so the degree to the number of variables. So the critical point system for a generic polynomial, it's n polynomials and n variables of degree d, so you get basically d to the n solutions. And so this is something that we're fairly happy with. Maybe you could, if you could improve this separation of moduli, you could improve this 4 to a 3, but this is quite good. But you'll notice that I say here probabilistic algorithm.
That's right.
And so
what type of probability?
yeah, so the reason for this, I'll explain it in a second. It comes from a representation for the algebraic set, for representing the critical points. So you could remove this probabilistic part and have deterministic, but then you'd have to do a Grosvenor basis calculation. And so the Grosvenor basis calculation, the complexity is much less understood. So we have an implementation in Maple, which I'll just run through. I'm going to go over time, so I'm just going to skip through a lot of the other slides to go to the showing the code. So you can make this deterministic, but then you lose this complexity result. And it's not really important how all this stuff down here, but there is some way of we exactly encode it by integer polynomials and roots of another integer polynomial. So I'm sorry, I'm going to have to go quite quickly through the last slides just to get to that.
So what are the things that make you interested in worst case complexity analysis?
Well, I mean, really what we are more interested in is just developing an algorithm that we can actually implement, because people don't want to know multivariate singularity analysis. They just have some sequence specified by a rational function that they want to put into Maple and get back the asymptotics, right? So to give these complexity results, basically what we did is we gave the first complete algorithm to do it. We didn't say like, oh, you should find these minimal points and you should find these critical points and then the asymptotics will be this. We said, here's how you would actually compute them exactly.
So what makes you being interested in the worst case complexity analysis?
Well, I mean, when we developed the algorithm, we needed to trace through. So you might also wonder why we did bit operations instead of just arithmetic operations. But basically, everything comes down to deciding certain algebraic equalities and inequalities. And so the idea is that we're going to use the symbolic numeric method. So we're going to work numerically, and we need to know how much precision we need to work to numerically. And so to do this, we had to keep track of all the degrees and coefficient sizes of all the polynomials that appear in our computations. So just to develop the algorithm, we basically had to keep track of everything, which would give us the complexity.
So your result, you're saying, is just used internally in the algorithm?
Yeah, I mean,
okay.
So this is also just people are interested in the complexity of finding these things, right? And I should also mention that we actually give bounds on the degrees and coefficient sizes of these polynomials or rational functions that appear in the asymptotics. So we can also give algebraic and arithmetic constraints on the constants that appear in asymptotics of these types of rational functions as well, which people need.
And so I didn't get the answer to the question regarding what kind of probabilistic algorithm.
Yeah, so I'll say this in a second, but basically, so we have this algebraic thing, semi-algebraic thing, and this is what we want to decide. So we want to represent our algebraic set, and we use something called the Kronecker Representation, which goes back to Kronecker's work in the 1880s. And basically, you introduce a new variable, which is a generic linear form, which is where this sort of randomness is coming in, as a linear combination of your old variables, and then you write your old variables as rational functions in your new variable, where the denominator is something special, and your new variable is encoded as the roots of a square-free polynomial. And the point is that you have good bounds on the coefficient sizes and degrees that appear here. And so we're going to work symbolic numerically, and so we want low coefficient degrees in particular so that we can not work to very much precision to decide the things that we need. So this goes back to Eric Schost and his PhD thesis. And so this is where the probabilistic part comes in, is computing this type of representation. So there's one algorithm by Justi, and Selby from 2001, where they gave, it's known as the geometric resolution algorithm. And there's a more recent paper by Mohab Safi-Aldin and Eric Shost, where they gave a homotopy-based algorithm. And so the randomness comes from this. So if you really want to know everything about it, you can look at this paper for computing Kronecker representation, and you can see exactly the model.
So is this a Monte Carlo algorithm?
I can't remember. You'd have to.
So can the user try the probability of correctness or not?
No.
No.
So anyway, in our implementation, we don't use the probabilistic thing because there isn't really a good implementation of this Kronecker representation. We just use Grosvenor bases. So it's so in our implementation, there is no probability. It's just deterministic. Yeah.
It's not clear what the actual statement is, right?
Yeah, you should.
The probabilistic is not.
Yeah. You should look into here to see the full details. And in the thesis, it gives also a bit more. It gives their full results on sort of what happens, but. Yeah, and so we also have a result if you remove, so everything, all the assumptions you can check except for having non-negative coefficients. So even in the univariate case, it's still open how to decide this in general. So that's a very strong one. And we can remove that assumption to get only verifiable assumptions, but then you go from HD to the 4n to something like HD to the 12n, which is quite a bit less practical.
And so it finds something. Is there certification?
No. There's not. So if you have this probabilistic algorithm, you don't fully know that it's correct, yes. But of course, as I said, the implementation doesn't have these difficulties because it uses Grosvenor bases. So the idea is that we reduce everything to polynomial equalities and inequalities, and we keep a close eye on the degrees and coefficient sizes so we can work numerically to sufficient precision. So I'm basically out of time, but I'll just show you. So this is not really important. If you look at this rational function, we have this implementation in Maple so that you can give the polynomial and say the variables, and it outputs the asymptotics. So the asymptotics are what you get when you set u to be the root of this polynomial, which is approximately this. So it's the unique root that agrees with this to some number of decimal places. And this is, again, as I mentioned before, these binomial sums appear quite frequently. So here's an example of a binomial sum from a paper in 2015, and the point of this paper was to show that you have this asymptotic expansion, but actually you can do this completely automatically. So there's a very nice package by Pierre Lerez, who is, again, another PhD student of Bruno Selby, that you can take in a binomial sum and it will give you, after some small conversion, a rational function that the sequence is the diagonal of, and then you can use our package to get asymptotics, and you can find this and this, and you can also compute higher order terms, I should say, not just the leading term. I just am only showing the leading term here. And then you recover this result. So, sorry, I think I maybe went 1 or 2 minutes over time, so just to sum up, these rational diagonals are a very efficient way of encoding many different sequences, as we saw, and they're it's becoming a very big theory right now, and in particular, people are very interested in actually computing these things and coming up with algorithms that can be implemented so others can use them. And so we have now the first complexity results and effective algorithms, but we want to relax our assumptions and of course make the computations more efficient. So we can use better results from unbounding these algebraic quantities that come up or using symbolic numerics. And also if you want to relax these assumptions, then you have to use different work from, for instance, the stratification of algebraic varieties if you're no longer a smooth manifold, or tools from real algebraic geometry, so things like minimizing polynomial equations over semi-algebraic sets, etc. So depending on how you want to relax it, it could be, it will be used by more and more people, but you need to bring in new theoretical tools. If you're interested in, you can look at this thesis for many, many details, or if you just want to see a little overview of the computation, you can look at this from ISAC, and we have a full paper which should be out soon with some more generalizations and things like that. Thank you very much for your attention. Sorry I went a little over.
Could, for example, it may not make sense, but I'm just asking, all right? Could the Gaussian elimination algorithm be coded as a lattice path problem?
Cool. I'm not sure. That's interesting.
Why do you make that connection? I don't see that connection at all.
Well, so you got a matrix, right? And you want to rewrite it, let's say in row echelon form or whatever. And so you have to do pivoting, elimination. So it looks like that there are moves
Yeah.
in
Yeah.
some way. I mean, in the way that you go horizontal, you go vertical.
Yeah.
I mean, in that sense.
I mean, I can see that, yes, but.
And the reason is the worst case complexity of the Gaussian elimination is given by a two variable recurrence,
Okay.
where the solution, even though I found it, I don't know this term analytic combinatorics, but I was using some not so kosher analytic method.
Yeah.
I can't justify how I derive it, but once it's derived, I can prove it by induction.
Okay.
So I was wondering that whether that there might be other ways to look at the recurrence and understanding the solution more combinatorial.
Yeah, I mean, if you have a multivariate linear recurrence, it's very natural to think of this as some kind of lattice path problem because you have these sites and you have transitions between them. But of course, you don't have to think about things in terms of lattice paths to apply this analytic combinatorics framework. It's very
Well, one of the, the solution has the form of a double summation where the variables, let's say call it n and m, is actually appearing in the summation. It's a finite summation. So, and looks like that the way that this technique is using is that they're using series, so it's infinite. In other words, the parameters, the variables don't appear as the limit of a summation. So Kawas told me not too long ago that there's no combinatorial package that can handle that kind of summation. Is that correct?
Yeah, I mean, if there was one, Manuel would be the guy to know it. So, or Parson Schneider, right?
I was trying to come yesterday to his talk, but the weather doesn't help me. And when I try to do it, I can't. I think I sent a message. I don't have audio. So is the video posted?
It will be soon.
Okay, all right.
But you couldn't get audio yesterday?
Yeah, yesterday.
During a
No, I tried five. Sorry, I mean this is not that. So we will talk about that later.
More questions? Okay, thank you again.